Hello. We're going to begin our discussion on the differential equations of motion for fluids with the conservation of mass. And we're going to start finding these differential equations with the control volume equation. Now, these differential equations are going to allow us to come up with detailed models of flows where we can look at the parameters as they change throughout the system. So we're going to start with this cubic control volume, and it's infinitesimally small. We have dx, dy, and dz as our lengths of our sides for our cubes. And we're going to take our CV equation and we're going to convert that surface integral into a summation. We're going to assume that the velocity differences over that face of a cube are small, so we can approximate the velocity with the average velocity. And when we do that, we can convert this surface integral into the summation over each of the 6 faces of the cube. Now, we can then substitute that into our CV equation to look something like this. Now, we're also making the assumption that the volume is small enough that the density is approximated by the average density in the cell. So in this equation, this is the average density in the cube or the cell, and this is the cell volume. So this gives us the mass. This is the mass flow rate in, and this is the mass flow rate out. Here, this is just 1D. We only consider the x direction. However, we can also add the y and z directions. So we would have y plus dy, y minus dy, z plus dz, and z minus dz. And once we've done that, we can divide through by dx, dy, dz. And that gives us something that looks like this. Now, here we need to have the density and the velocity on the faces of the cube. So you can see it's x plus dx over 2. So dx over 2 is the left face or the right face of the cube, centered on position x. So in order to do that, we use the Taylor approximation. On the negative face, we use the gradient and the value of dx to get the value at that point. And we do the same thing on the positive side, only we have the opposite sign. When we do that, we can substitute these definitions into the previous version, and what we end up with is an equation that looks like this. So we have our time derivative, which is our storage of mass. We have the mass in minus mass out on each of the x, y, and z coordinate directions. And we can simplify this in vector form by using the gradient operator, gradient del rho v. So this would be d dx dotted with rho times u comma v comma w. So this gives us a more compact version of our conservation of mass equation. Now there's only a single equation here because of the dot product. We have to add all the terms together. Now, this is a useful equation. It's a very important equation. However, when we're solving problems, oftentimes we want to simplify it. So we have a few simplifications. The first one is incompressible flow. Now, for an incompressible flow, the density is constant. So d density d time is 0, and density can be removed from the gradient. So we end up with this very simple equation, which is del dot v equals 0. So du dx plus dv dy plus dw dz is equal to 0. So it gives us a way to relate all of the different components of the velocity to each other. Of course, for steady flow, we can neglect the time derivative. However, steady flow is not enough to assume that the density is uniform, so we have to include density in the gradient operator there. We can also convert this into cylindrical or spherical coordinates. So cylindrical coordinates, we might be interested in, say, flow in a pipe. So then we can solve this equation over a variety of different coordinate systems.